Chapter 7, Linear Regression. Example 1. During the evening rush hour of August 1st, 2007, an 8-lane steel truss bridge spanning the Mississippi River in Minneapolis, Minnesota, collapsed without warning, sending cars plummeting into the river, killing 13 and injuring 145. Although similar events had brought attention to our aging infrastructure, this disaster put the spotlight on the problem and raised the awareness of the general public. How can we tell if bridges are safe? Most states conduct regular safety checks, giving a bridge a structural deficiency score on various scales. The New York State Department of Transportation uses a scale that runs from 1 to 7, with a score of 5 or less indicating deficient. Many factors contribute to the deterioration of a bridge, including amount of traffic, material used in a bridge, weather, and bridge design. New York has more than 17,000 bridges. We look at data on the 194 bridges in Tompkins County. One natural concern is the age of a bridge. A model that relates age to safety score might help the DOT to focus inspectors' efforts where they are needed most. Is there a relationship between age of a bridge and its safety rating? So we want to check all the conditions, and we're going to go ahead and do what's called a regression analysis or regression model, as you saw from your reading, that will tell us what that relationship is. So it gives us a little more detail. Usually we'll be more clear on the instructions, find the regression model, or state what the relationship is, something like that. As you can see, we have a scatter plot provided here. First thing we want to do that we know when we have a scatter plot is talk about the shape, the strength, unusual, form, direction, so our duffs. Looking at the scatter plot, we start up here. At an age of 0, you have scores of 7. At an age of 120 years, it looks like we have really low scores. So that's where we're going to begin. It also looks like, so it's a negative relationship, it looks pretty linear. The points are maybe a little bit spread out, kind of in the middle, but it's still pretty strong. I mean, that's, for real data, that's going to be pretty strong. So let's go ahead and write that up. The scatter plot of bridge age and safety rating remember, you always want context. That's why I'm starting off this way. I'm getting that context in right at the beginning. Context, context, context. So the scatter plot has a moderately strong, negative, linear association. Yes, we generally just deal with linear, but you still have to state that in there specifically. Okay, now we want to check our conditions. We'll talk about the unusual in just a moment. Both variables, our explanatory variable is age, which is in years. Safety score is a score, which is on that 1 to 7 scale. So those are points. Both variables are quantitative data. And the scatter plot looks straight. No outliers are evident. So I can proceed with a linear regression model. Okay, so from your reading, you'll recall that the regression model is y hat equals b naught plus b1 times x, which is your explanatory variable. And b1 equals the correlation times the standard deviation of the y variable divided by the standard deviation of the x. B naught is your y-intercept, essentially, and it's y bar, the average value of your response variable, minus b1, which we're actually calculating the slope when we find b1, the slope of the regression line, and x bar, the average value of the explanatory variable, which in this example is age. Remember, we're creating a model. It's going to have predictive power, but the model will be wrong. It gives us a good estimate, but it will be wrong. They'll have values above or below the line when we make it. Because essentially what we're doing here is we're writing the equation of a line that goes through here and fits the data as well as it can. If you notice, there are going to be values above the line, and there will be values below the line. We might get some that are on the line, but for the most part, they're going to be above or below. It's going to be wrong, but it still gives us some really useful information. It still has a good predictive power. So let's go ahead and calculate this. All of this information is provided for us. So correlation is negative 0.681. We have our y bar, our standard deviation of the x, our x bar, and the standard deviation of the x variable right there. We have y bar and standard deviation of the y variable below that. With these, you're either going to have a computer printout or the raw data that you can type in the calculator. You're not going to have to do everything by hand, but it's still important to know how to do these calculations. There will be examples where you might have the model and you need to calculate the standard deviation, so you have to work backwards. You have B1 and you might know the standard deviations, but you need to find the correlation, something like that. So we know our correlation is negative 0.681. The standard deviation, which is given, is 1.0297. The standard deviation of the x variable, or explanatory variable, is 30.75. And when we calculate all this, use a calculator, preserve as many decimal points as you can. It's okay to leave this number in the calculator, store it, and just use it again, and then only round at the very final product. But there's your slope, negative 0.0228, and we'll talk about in just a moment what that really means. Okay, so now to finish our regression model, we need the y-intercept. My y bar is 5.2779 minus b1, which is this negative 0.0228 times x bar, the 44.9, and this comes out to be 6.30162. And now we're ready to write out the model. Our model is y bar, keep saying y bar, y hat, that's a prediction. Y bar is always a mean, y hat is a prediction. Keep that in mind. Whenever you're doing this model, you should have a hat there. So 6.301.6. We'll just go 4 places with this since we went 4 with the slope. And then minus, yes, I know it's b naught plus b1x, but since our slope is negative, that becomes a negative. So negative 0.0228 0.0228 x. Looks good, right? No! That is not how we write our answer out. No! We're going to use context. You could make the above work if you did a legend, but it's much better to go ahead and just use the context in the problem. Y bar is our response variable, which if you look over at the model, the response variable is safety score. So don't put Y bar, we're going to write down safety score. And of course, it's a prediction. So we're going to put the hat over it. Equals 6.3016 minus 0.0228. And now we're not going to use x. We're going to use the explanatory variable, the x variable, which is age. Yes, this is good. This is what we want. That is the regression model. Now, the problem asked, is there a relationship between them? There is, and let's say what it is. So, there does appear to be a relationship between age and safety score. I kept saying just age, but we need to make sure we show that it's bridge age in there to include the full context. Without that, on an AP exam or a lot of our tests, you would miss some points there. Okay. On average, so this is important. We're going to talk about what that slope means. On average, okay, remember what slope is. Slope is rise over run. We remember that from Algebra 2, Algebra 1, pre-algebra, whatever. You've been doing this for years. So my run is age, my rise is score. So for every 1 unit of age I increase, the score rises by my slope there. So that's what we're going to write down here. Okay, on average, we would expect a bridge's safety rating to, remember this is rise over run, so we're talking about it going up or going down. It's negative, so it's going down. So we would expect the bridge's safety rating score to drop by the slope, which was at negative 0.228, points for every year of age. the bridge has existed. This is useful because we would know about when it drops below 5 points. On average, it looks like every 50 years or so, but it would have gone down 2 full points. So that's very important information for investigators. They know if a bridge is only 10 years, they're probably in pretty good shape. They might not need to check that as often. But older bridges, they know they're going to need to check.